Hello everyone, I am Abhijit Lal, Assistant Professor, Department of EEE, BIT Durg. Today we are going to study about the instruments in insulation testing. So this will be the contents for today's lecture. That is, what is good insulation, how insulation resistance is measured, how to interpret resistance readings, factors affecting insulation resistance readings, types of insulation resistance test, and connections for testing insulation resistance of different type of electrical equipment. So let us start with the good insulation. Which insulation is called as good? So every electric wire in a plant, whether it's in a motor, generator, cable, switch, transformer, etc., is carefully covered with some form of electrical insulation. The wire itself is usually copper or aluminum, which is known to be a good conductor of the electric current that powers your equipment. The insulation must be just the opposite from a conductor. It should resist current and keep that current in its path along the conductor. The purpose of insulation around a conductor is much like that of a pipe carrying water, and Ohm's law of electricity can be more easily understood by a comparison with water flow. So the figure 1 shows the comparison of water flow with electric current. So in a figure 1a, a water pipe is shown in which the water is flowing and the water is pumped through a electric pump and flowing through a pipe, and a leakage is present from which the water is coming out. So it is similar to an electrical system. In figure 1b, we can see a conductor is used in which a current is flowing. It is noted by current I, and the voltage applied is E, and in that conductor an insulation is provided, and at a point there is a deterioration in insulation by which a leakage of electrical current takes place. So the property of that conductor is to resist. For that the resistance is shown, and the material used for the conductor is copper wire. So in both the figures, that is 1a and 1b, there is a leakage. In 1a there is a leakage of water, and in figure 1b there is a leakage of current, which is called as electrical leakage. So in figure 1 we have shown the comparison. Pressure on water from a pump causes flow along the pipe, which is shown in figure 1a. If the pipe were to spring a leak, you would waste water and lose some water pressure. With electricity, voltage is like the pump pressure, causing electricity to flow along the copper wire, which is shown in figure 1b. As in a water pipe, there is some resistance to flow, but it is much less along the wire than it is through the insulation. The more voltage we have, the more current there will be. Also, the lower the resistance of the wire, the more current for the same voltage. No insulation is perfect, that is, has infinite resistance. So some electricity does flow along the insulation or through it to ground. Such a current may only be a millionth of an ampere or 1 microampere, but it is the basis of insulation testing equipment. Also that a higher voltage tends to cause more current through the insulation. This small amount of current would not, of course, harm good insulation, but would be a problem if the insulation has deteriorated. Now let us discuss how insulation resistance is measured. Good insulation has high resistance, poor insulation has relatively low resistance. The actual resistance values can be higher or lower depending upon such factors as the temperature or moisture content of the insulation, that is resistance decreases in temperature or moisture. The Mager insulation tester is a small portable instrument that gives you a direct reading of insulation resistance in ohms or mega ohms. For good insulation, the resistance usually reads in the mega ohm range. So here the insulation tester is called as the Mager insulation tester, by which the insulation of any electrical equipment can be calculated, particularly about the insulations used in all the electrical equipments. The Mager insulation tester is essentially a high range resistance meter or ohmmeter with a built-in direct current generator. This meter is of special construction with both current and voltage coils, enabling true ohms to be read directly independent of the actual voltage applied. This method is non-destructive, that is, it does not cause deterioration of the insulation. The generator can be hand cranked or line operated to develop a high DC voltage which causes a small current through and over surfaces of the insulation being tested, and it is shown in figure 2. So the figure 2 shows the typical Mager test instrument hooked up to measure insulation resistance. Here we can see a conductor made up of copper wire is used and a wire insulation is provided above the copper wire. So the Mager has 3 terminals, that is G, L and E. So the L point of the Mager is connected to the copper wire, L denotes the live wire, and the E point is connected to the insulation. So the meter shows the scale which gives the reading about the resistance. So this is how the Mager insulation tester determines or shows or measures the resistance of an insulation. So this current, usually at an applied voltage of 500 volts or more, is measured by the ohmmeter, which has an indicating scale. The figure 3 shows a typical scale on the Mager insulation, which is having more than one scale of different ratings. One is of ohm and another is of mega ohm. And the third scale is for the voltage measurement, that is voltage generated by the generator present in the Mager. So the figure 3 shows a typical scale which reads increasing resistance values from left up to infinity, or resistance too high to be measured. Now let us discuss how to interpret resistance readings. Some general observations about how you can interpret periodic insulation resistance tests and what you should do with the result is shown in the below table. So, in the one hand, the condition is given, and on the other side, it is mentioned what to do with that at that condition. So, first condition is fair to high values and well maintained. So, under this, no cause for concern. Second condition can be fair to high values but showing a constant tendency towards lower values. So, under this, locate and remedy the cause and check the downward trend. Next condition which can be obtained is low but well maintained. Under this condition is probably alright, but cause of low values should be checked. Next condition is so low as to be unsafe. Under this condition, clean, dry out or otherwise raise the values before placing equipment in service. Test wet equipment while drying out. So the following things should be performed under this condition. Last condition which can be obtained during test is fair or high values previously well maintained but showing sudden lowering. Under this condition, what we have to do is make tests at frequent intervals until the cause of low values is located and remedied, or until the values have become steady at a lower value but safe for operation, or until values become so low that it is unsafe to keep the equipment in operation. Now let us discuss about the factors affecting insulation resistance readings. The measured resistance of the insulation will be determined by the voltage applied and the resultant current. Here the voltage applied is denoted by capital E and the current or the resultant current is denoted by capital I. So by Ohm's law, the resistance will be equal to E upon I. There are a number of things that affect current, including temperature of the insulation and humidity. Let us consider the nature of current through insulation and the effect of how long voltage is applied. Current through and along insulation is made up partly of a relatively steady current in leakage paths over the insulation surface. Electricity also flows through the volume of the insulation. Total current comprises three components. First is capacitance charging current, second is absorption current, and third is conduction or leakage current. So the current measured by the insulation tester, it is the combination of all these three currents. Now let us discuss individually about these three current. The first one is capacitance charging current. So the current that starts out high and drops after the insulation has been charged to full voltage is called capacitance charging current. Next current is the absorption current. It is also an initially high current which then drops. So both this current, that is the capacitance charging current and absorption current, they starts at a very high pace but drops after some time. And the third current is the conduction or leakage current. It is a small value. A small, essentially steady current both through and over the insulation. So the figure 4 shows the curves showing components of current measured during DC testing of insulation. So this graph is drawn between the current and the time. The time is taken in seconds. So in this we can see the three components of the total current. The first is the conduction current, second is the absorption current, first is the capacitance charging current. It is at a very high value at the starting time, that means when the seconds is very low, but it drops quickly to a very low value. Similarly, the absorption current is very high at the starting, but it drops slowly, whereas the conduction or leakage current, its value is very less at the starting, but as soon as the time increases, its value increases and at a particular time it gets constant. So these three currents collectively combined form the total current measured through the insulation tester. From figure 4, it is clear that the charging current disappears relatively rapidly as the equipment under test becomes charged. Larger units with more capacitance will take longer to be charged. This current also is the stored energy initially discharged after your test by short circuiting and grounding the insulation. So always take this safety measure. Further, the absorption current decreases at a relatively slow rate depending upon the exact nature of the insulation. This stored energy too must be released at the end of a test and requires a longer time than the capacitance charging current, that is about 4 times as long as the voltage was applied. So these are the reasons, that is the stored energy due to which the capacitance current and the absorption current is very high at the starting. So that should be released, as it is mentioned, it must be released at the end of a test so that the next test, for the next test, the value is at normal value or at the normal range. With good insulation, the conduction or leakage current should build up to a steady value that is constant for the applied voltage as shown in figure 4. Any increase of leakage current with time is a warning of trouble. With a background now of how time affects the meaning of instrument readings, let's consider three common test methods. So, first method is short time or spot reading. Second method is time resistance, and third is step or multi-voltage test. So, let us discuss in detail the types of insulation resistance test. So, first test is short time or spot reading test. In this method, simply connect the Megger instrument across the insulation to be tested and operate it for a short specific time period, which is around 60 seconds recommended for this test. As shown schematically in figure 5, simply picked a point on a curve of increasing resistance values. Quite often the value would be less for 30 seconds, more than for 60 seconds. So, bear in mind also that temperature and humidity as well as condition of your insulation affect your reading. So, the temperature and humidity also plays an important role which changes the reading of the insulation when it is tested from different methods. So, the figure 5 shows the typical curve of insulation resistance measured in mega ohms with time for the short time or spot reading test method. So, short time method is also called as spot reading method because it is performed just for a 60-second time, and the graph is plotted between the resistance and time. The resistance is measured in mega ohms. So, characteristics is obtained. So, the value is read and recorded at 60 seconds. So, the resistance is measured till 60 seconds and the characteristics obtained at the point of 60 seconds is determined, and that will be the value of insulation resistance. If the apparatus under testing has very small capacitance such as a short run of house wiring, the spot reading test is all that is necessary. However, most equipment is capacitive, and so very first spot reading on equipment in plant with no prior test can be only a rough guide as to how good or bad the insulation is. For many years, maintenance professionals have used the 1 mega ohm rule to establish the allowable lower limit for insulation resistance, and the rule may be stated as insulation resistance should be approximately 1 mega ohm for each 1000 volts of operating voltage with a minimum value of 1 mega ohm. Now, let us discuss the second method, which is time resistance method. So, this method is fairly independent of temperature and often can give you conclusive information without records of past tests. It is based on the absorption effect of good insulation compared to that of moist or contaminated insulation. You simply take successive readings at specific times and note the differences in readings as shown in figure 6. Tests by this method are sometimes referred to as absorption tests. So, the figure 6 shows the typical curves showing dielectric absorption effects in a time resistance test made on capacitive equipment such as a large motor winding. Again, the graph is plotted between the resistance taken in mega ohms and the time measured in seconds or minutes. In this, we will obtain two characteristic 1 and characteristic B. characteristic, or it is mentioned as characteristic A and characteristic B. So the characteristic A shows the insulation probability, is it okay or not, and second characteristic shows the moisture and dirt, it may be present or not. So in this way, this method gives us the two values, that is about the condition of the insulation, and second the moisture and the dirt content in the insulation. Note that good insulation shows a continual increase in resistance, that is less current seen in curve A, over a period of time in the order of 5 to 10 minutes. This is caused by the absorption of current we spoke of earlier, that is good insulation shows this change effect over a time period much longer than the time required to charge the capacitance of the insulation. If the insulation contains much moisture or contaminants, the absorption effect is masked by a high leakage current which stays at a fairly constant value, keeping the resistance reading low, as from the Ohm's law R is equal to E by I. The time resistance test is of value also because it is independent of equipment size. The increase in resistance for clean and dry insulation occurs in the same manner whether a motor is large or small. You can therefore compare several motors and establish standards for new ones regardless of their horsepower ratings. Now the figure 7 shows how a 60-second test would appear for good and perhaps bad insulation. When the insulation is in good shape, the 60-second reading is higher than the 30-second reading. A further advantage of this double reading test, as it is sometimes called, is that it gives you a clearer picture even when a spot reading says the insulation looks fine. Now the figure 7 shows a typical card plot of a time resistance or double reading test. In this curve we can see the insulation resistance at different values of time. In this the characteristics two curves are shown. The upper one is showing that the insulation is good, and the lower curve shows that the insulation may be weak, or a better watch should be done so that the insulation do not get deteriorated completely. Now the last method is step or multi-voltage test. In this method, you need a multi-voltage Megger instrument to apply two or more voltages in steps like 500 volts and then 1000 volts. Look for any reduction of insulation resistance at the higher voltage. If the resistance is lower, it's a sign of an insulation weakness that shows up only at the higher voltage. Now the figure 8 shows an example in which instead of progressively increasing the voltage, you first test at a low voltage such as 500 volts, and then after discharging the sample you test again at a higher voltage such as 2500 volts. So the figure 8 shows the typical curves with step voltage test. Again it is drawn between the resistance measured in mega ohms and the time in second. So in this method again we will get the two characteristics. The first characteristic is obtained when the test is made with 500 volt, and the second characteristic is obtained when test is made with 2500 volt, which shows the insulation weakness. Any difference in the two tests in terms of mega ohms will show signs of weaknesses at the higher voltage, a warning to investigate further. As the conditions within the sample deteriorate, the higher voltage plot as shown in figure 8 will reduce in mega ohms compared to the lower voltage one, and its upward slope will be less. The theory behind the step voltage technique is a bit complex. Moisture and dirt in insulation are usually revealed by the test at voltages far below those expected in surveys. However, effects of aging or mechanical damage in fairly clean and dry insulation may not be revealed at such low stress. As is true with the spot reading and time resistance measurements, the step voltage method is more valuable when repeated on a periodic or scheduled basis. The step voltage method is particularly useful in determining the presence of excessive moisture or other contaminants in the insulation of equipment that is rated at voltages equivalent to or greater than the highest voltage available in a multi-voltage mega instrument. In other words, even though your highest voltage does not stress the insulation beyond its rating, a 2 voltage test can nevertheless often reveal the presence of such contaminants. Now let us discuss the different connections for testing insulation resistance of electrical equipment. Now let us discuss one by one the connections with different electrical equipments. So first is AC motors and starting equipment. So in this we can see a mega insulation tester is connected with the starter and the main switch and along with the motor. So one terminal from the mega is connected to the red or earth lid of the motor and the second terminal is connected to the main switch, and this is shown in figure 9. So connections for testing the insulation resistance of a motor, a starting equipment and connecting lines in parallel. Note that the starter switch is in the on position for the test. It is always preferable to disconnect the component parts and test them separately in order to determine where weaknesses exist. Now the next electrical equipment is the DC generator or motor. Again in this the insulation tester is connected with the DC motor through brushes or commutator, and one point is connected to the red or earth lid. So the figure 10 shows the DC generator and motor connected to the mega insulation tester. So with the brushes raised as indicated, the brush rigging and the filled coils can be tested separately from the armature. Likewise, the armature can be tested by itself. With the brushes lowered, the test will be that of brush rigging, filled coils and armature combined. Now the third equipment is the power cable. In this again the two terminals are connected with the live wire and the insulation. So connections for testing the insulation resistance of a power cable is shown in figure 11. When testing cable, it is usually best to disconnect at both ends in order to test the cable by itself and to avoid error due to leakage across or through switchboards or panel boards. Next is power transformer. Figure 12 shows the connection of Megger or the insulation tester with the power transformer. So the connections for testing insulation resistance of a transformer, high voltage winding and bushings and the high tension disconnect switch in parallel with reference to the low voltage winding and ground. Note that the low voltage winding is grounded for this test. Next is the AC generator. The Megger insulation tester is connected with the AC generator. With this connection, the insulation resistance will be that of the generator, stator winding and connecting cable combined, and the connection is shown in figure 12. To test either the stator winding or the cable itself, the cable must be disconnected at the machine. And lastly, the appliances, meters or instruments and the miscellaneous electrical apparatus. It is shown in figure 13 how the Megger insulation tester is connected with these equipments. So the connections for testing an appliance, the test is made between the conductor, the heating unit, motor etc. and the exposed metal parts. The apparatus must be disconnected from any source of power and placed on some insulating material. So, in today's lecture we have studied about the insulation testing procedure and how it is tested for different equipments, their connections and the methods. Thank you.